on example 3, part A. For f of x equaling 3x squared as x approaches infinity, what does f of x approach? Well, when we first learned to find limits, we looked at it both numerically and graphically. So let's just build a table of values. We'll just start with, let's say, 1, and then just keep increasing our x value, maybe even by factors of 10 or something like that. And you can see when we plug those in and look at our f of x values, they seem to be getting bigger and bigger and bigger and bigger. All right, so implying that f of x is approaching infinity, right? Well, we could take a look at the graph of this thing. Hey, that's a parabola. We've been graphing these things for years. It's like, it's skinnier. It's skinnier than the parent function. That's pretty easy to graph. And as x approaches infinity, as I move closer and closer to the right-hand side, I can see, of course, that my in behavior is going upwards. It's increasing without bound. And this is an example of an infinite limit at infinity. And I would write the limit as x approaches infinity of 3x squared is equal to infinity. And since it's equal to infinity, I understand that means that it does not exist due to unbounded behavior. It's just a nice way of saying, describing the in behavior of this graph as it's going upwards, right? Okay, well, let's look at, say, the left side of this thing. So on the left side of this thing, just as x approaches negative infinity, it doesn't really matter when we're plugging in these negative numbers that are decreasing. I'm squaring those numbers, and I still get the exact same values. Come on, it's a parabola. It's symmetric to the x-axis. It's a referee. Both ends are pointing upwards. So this is another example of an infinite limit at infinity. Limits at infinity are talking about the x values that are underneath the limit, that it, in this case, is decreasing without bound. Infinite limit at infinity means that the f of x values are also increasing without bound. And again, this refers to the in behavior. So this is an example of an infinite limit at infinity that refers to the in behavior of the graph. But wait, there's more, because example 3 is just not long enough. So example 3 part C. For f of x equaling 3x squared over x squared plus 1 as x approaches infinity, what does f of x approach this time? So instead of just a polynomial function, we have ourselves a rational function. So things that are associated with rational functions are like, we got some asymptotes, probably, maybe vertical, maybe horizontal asymptotes. So we'll do the same thing that we did on the previous ones. We'll look at a table of values, plugging numbers in that are getting increasingly bigger, and see what the f of x values are approaching. Okay, so we can see that as x gets bigger and bigger and bigger, f of x is not getting bigger and bigger. It seems to be approaching the number 3. So this is not an infinite limit at infinity. This is a finite one. And specifically, this refers to a horizontal asymptote. And I would write something like the limit as x approaches infinity of f of x is equal to 3. Again, this is an example of a finite limit at infinity, and it refers to a horizontal asymptote for that graph. So you might remember from pre-cal and from algebra 2 that we could have gotten that horizontal asymptote of 3 by just looking at this function. The powers are the same, which means that they grow relatively at the same rate. It's just that the top is going to grow at 3 times that rate. So this should be approaching the number y equals 3. Okay, so in limit notation for that previous one, this is what we wrote. So the limit as x approaches infinity, this is a limit at infinity, because we're approaching infinity, of 3x squared over x squared plus 1 is equal to 3. And it's a finite limit at infinity. Remember, finite just simply means that it ends someplace. You can actually count to this number, given enough time and willpower or whatever. And this refers to a horizontal asymptote for that graph. So let's kind of informally define this limits at infinity. So we have limit as x approaches either a positive or negative infinity of f of x equaling L. This is a finite limit at infinity. It's going to refer to a horizontal asymptote. This finite limit of infinity means that f of x approaches some unique number L, a 3, a 4, whatever, as x increases or decreases without bound. And as I said graphically, that this refers to a horizontal asymptote. So let me just take a second and distinguish the horizontal asymptote from the vertical asymptote in terms of some sort of limit. So come over here so I can write on the screen just a little bit and maybe get an extra little page going on. What are we at right here? Add a page. All right, so that we could talk specifically about the difference, like what this looks like in terms of a limit. So here's the vertical ones. So let's just kind of look at maybe a graph first. And I would have, let's get some colors in here, maybe, and then maybe have something like this. And this is an x value at that vertical asymptote. We could say that, who knows, maybe it's like the number 1. And I would write something like the limit as x approaches 1 of f of x is equal to infinity. This is not a limit at infinity, but it is an infinite limit because it increases without bound, and it's referring specifically to a vertical asymptote. All right, so then when we look at the horizontal one, on the horizontal one, taking a look at some sort of graph. So this time we might have a horizontal asymptote thusly, and maybe my graph does something like, and we'll call that number 1, just like we called the other one number 1. And you'll see how these things have some similarities and some differences here. So this time, whenever I write my limit, it's going to be limit as x approaches infinity of f of x is equal to 1. And so for a horizontal asymptote versus a vertical one, notice that the x and the y values basically just switch places. And I want to be able to easily recognize the difference between these two things and associate this one with a vertical asymptote for a graph and this one with a horizontal asymptote from a graph.